There we go. All right, let's get into our tutorials. Optical water classification. Well, you can see it here, but it doesn't quite translate into the hub here. Um, all right, so in a previous tutorial, we had focused on, make sure this gets through. Yeah. Extracting those kind of sensitive metrics of change in the ocean using the hyperspectral reflectance. And we had those derived indices like AVW and brightness. So we're going to stay on that same theme, but take a kind of slightly different, more categorical approach. So this time we're going to be talking about optical water types, or OWTs, rather than tracking individual bands or indices. Optical water type classification lets us kind of group ocean waters based on the shape of their reflectance spectra. So the idea is pretty simple. Waters that look optically similar tend to share underlying physical or biological properties is sort of the assumption here. So a few years ago, our very astute NOAA colleague, Jinwei Wei, compiled a large global database of in situ and simulated hyperspectral reflectance measurements. And using k-means clustering, he showed that the marine waters around the world can be reasonably grouped into those 23 water masses. I'll just show it here so we can see it. Yeah, into these various shapes, these 23 optical water masses. So those 23 average spectra become kind of a reference library. With hyperspectral sensors like PACE, we can then take the spectrum at every single pixel that we have and ask which one of these 23 shapes does this most look like. Once we answer that, then we can assign that pixel an optical water type. The big advantage here is consistency. So instead of comparing raw spectra or derived products that might sort of vary in subtle ways, we're placing our observations into a fixed, globally defined classification framework that kind of clearly delineates waters with distinct optical properties. It's, akin to being on a kitschy, tour group, everyone wearing the same bright t-shirt. Suddenly your patterns kind of jump out, and it's a little easier to see how things organize in time and space when you can put things into this perspective. Another note that this is another one that's not currently a standard distributed PACE data product. Probably not likely to be, but it has generated a lot of interest within NOAA fisheries. So in this tutorial, we just want to extend that capability to you all and show you how straightforward it is to implement if you would like to use it. So here's the plan. We're gonna load these 23 reference spectra that Jinwei graciously provided for us. We're going to apply a very simple but effective spectral matching technique, which I think in itself is a pretty useful thing to know about, even outside of this application. And then we're going to assign each PACE pixel into one of these optical water classes. And then once we do that, we can generate full maps of hyperspectral optical water types. All right. So we'll dive in and start messing around with some PACE data. So hopefully by the end of this, we will have by the end of this, we calculate the cosine distance between the PACE spectra and a reference spectral library. That cosine distance is going to be our sort of spectral matching technique. Assign the optical water types to PACE data. We'll make a map of that. And then we'll compare the observed PACE spectra against this reference spectra and see how well of a job it did. And then we'll try our own hand at k-means clustering, because we're in Python and we can do that. So we'll work with it there. This is where a lot of kind of the fun pattern finding really starts for me. I love it. So, and I'm trying to run things that aren't. All right. Sorry. Let's go ahead and get logged in. We're going to grab the reflectance spectra. We'll keep at this 0.1 degree since we're kind of in. Look at me. Let me kill my. Shut down all my kernels since I have a bunch of memory stacked up here. Don't be like me. Remember where your memory is. Okay. Disconnected. So restart the kernel. There we go. Now we got some space. You shouldn't need the full 4 gigabytes. I think two does just fine here. All right, so grabbing this level 3 paste file. When I was putting this together, so it's kind of originally tended to come right after the remote sensing reflectance, but kind of switch things around a little bit. But we already did cover some of this, but I think it helps worth repeating, because if this is all new to you, repetition really can't hurt. Some of these key differences between the level 3 versus level 2, the mechanics are just different enough that you might make you kind of bang your head against the wall if you're not expecting them. So I've already done considerable amount of that head banging for you. So here's what came out on the other side of this. So the short name here in level 3, this is product base. So it's RRS or chlorophyll, rather than the broader product suite names that you would use in level 2. You grab the whole AOP bundle, you grab the whole BGC bundle, and that has POC and chlorophyll and fluorescence line height in it and stuff like that. So you grab sort of individual products. It's still a 3D reflectance product, but you kind of deal with it in that way in the level 3 files. The bounding box isn't needed for like it might be in level 2, because the level 3 products are already spatially mapped. They're global. Even if you try to give it a bounding box, it won't break, but it's not going to do anything. It'll just give you it'll just spit back the global file. The granule name now encodes both the time and the spatial averaging as well, spatial resolution as well. So you could do year, YR, MO for month, 8D for 8 weekly composites, DAY or day for daily. I think seasonal, or like SNSU is summer season. It'll average 3 months together. SNSP for spring. So those are all the different sort of temporal things you can pass. And we have 4 kilometer available here, 4, 9 kilometer, and then the 0.1 degree, which is I think like a roughly 11 kilometer, changes with latitude and all that. But okay, so yeah. Anyways, it's not too nuanced, but it's just different enough from level 2 that it can make things worth calling out explicitly, as well as when you open these files as well. You don't need to extract data trees, where with level 2 files you have data trees where you have to pull out your variables from geophysical from various groups within that. Here it's just kind of organized a little more sort of upfront. So when we define a data set, we can pull the reflectance straight from that data set. We don't have to find the groups within. All right, long explanation there, but okay. Did I grab that? All right, let's load up our libraries. All right. So we're going to start here. I'll go ahead and load up our remote sensing reflectance. Subsetting this is really helpful too. We can't subset. I mentioned you can't subset as you're querying through Earth data access like you can with level 2 files. But if you don't want to work with the whole globe, a good thing to do, since we have this slice function, is just narrow down the area that you're interested up front. And now you have a much smaller X array. When you start dealing with this, you're dealing with a smaller X array. You're not having to deal with the whole global file. So this RS subset's really good for that. All right, so we're going to load up these 23 optical water types. This is just a CSV file that has just a bunch of reference spectra here. Their reference spectra are observed every 1 nanometer. PACE is not quite at 1 nanometer. It's kind of 2.5 nanometer, and there's some that are sampled a little closer than others. So the next step is to identify the wavelengths that both data sets have in common. So we convert the PACE wavelengths to strings, and then we match that to the CSV column names, and then intersect the two sets. So this ensures that both the satellite spectra and the reference spectra kind of are living on the same wavelength grid. So this is really critical for any sort of spectral similarity metric here. All right, so here's the 136 common wavelengths. that were between the two. So these are all the pace wavelengths here that we grab between 400 and 700 nanometers. So, okay, yeah, then we could subset the reflectance spectra and the satellite spectra just to those bands, which is what we're going to do here. So there's another important aspect here, the normalization. And where's that? Oh, sorry, there's a whole bunch of stuff here I'm skipping over. Okay, the normalization, which happens here. Jinwei defined their optical water types based on the shape of the reflectance spectra, not its absolute magnitude. We kind of talked about that in the first reflectance aspect. They normalize the spectra, so we're looking at just shape differences. That's how these clusters are being made. So we briefly reshaped the satellite data. When we did it with the reflectance, we normalized to the area under the curve. This is just a different way of doing it. This is how he did it, so I'm going to go ahead and just be consistent with what was done in the paper here. But basically, if you want to normalize, you're just dividing your reflectance spectrum by this this normalization component here to get them all on the same relative brightness level, essentially. All right, we've seen this before here, but we're effectively how should I say, it's like we flatten the spatial dimensions in a single pixel axis here. So it gives us a 2D sort of array of shape that is pixels by wavelengths instead of the sort of 3D lat long, so this lets us compute all the comparisons in sort of one vectorized operation. Otherwise, we're going 4i, j, and going through every pixel. So this by flattening this, we're just sort of reshaping it so that we can vectorize this, and just sort of when we do any sort of math to it, it's happening to the entire array sort of all at once. So with everything aligned and normalized, now we compute the cosine distance here. This is just 1 minus the dot product between each satellite spectrum and each reference spectrum. Without getting too deep into the math, the cosine distance basically tells us how similar the shape of the two spectra are. So and it's independent of their absolute magnitude. So it does this by comparing the angle between the pace spectrum and each of those 23 reference spectra in the spectral space. So the idea is straightforward. The smaller the cosine distance, that means that it has a closer spectral match. So for every single pixel, we compute that distance to all the 23 reference spectra, and whichever one comes out the smallest is the optical water type that we assign to that pixel. So that's it. This is kind of where all the magic is happening here. So we're just pulling the smallest cosine distance compared to those 23 types. More things. So when we vectorize this, we do have to send this back into that 2D shape here. So we're reshaping this back to a 2D map here, based off of the lat long. So we put this in that sort of wavelength by a whole sort of 1D array of pixels and wavelengths. Now we're putting that back into that array here, so we can map it essentially. All right, so let's make this optical water type here from one of our images. We're just a basic plot that we've made before with a little nuance here that I'll go through just to get this color bar is a little tricky here, but here you can see the output here. So making optical water type map for our single monthly image. So yeah, getting the water classes all lined up can be a little tricky. The boundary norm here basically takes care of it for us to kind of make sure that all the 23 classes gets its own color and that the colors are spread evenly across the full range of class IDs. So first we use this NP arrange, which very irritatingly has input arguments of start and stopping number. So if we want 24 boundaries here, we actually have to specify it to stop at 25, and it will be 1 through 24. I hate it, but if you're wondering why we suddenly switch to 20, anyways, but we're also talking about 24, right? And I've been talking about 23 classes. Why am I talking about 24 for this? Because when we have 23 classes here, you need 24 boundaries, because each class is an interval between 2, 1 to 2, 2 to 3, 3 to 4. So our 23rd boundary needs to basically go from 23 to 24, which is how we make these sort of increments here. So 23 to 24 is, and hence why. So I hope this isn't too tedious, but I don't want there to be too much black magic behind what's going on behind the curtain here. So it's all in the weeds, but it's these little kind of things that are kind of challenging, but just want to demystify for you. Okay, so we have this cool map. We have all these water classes here, but it's still a little abstract. We don't know what it means. So let's take a gander at what each of these colors actually contains. Excuse me. So we matched every pace spectra in the image to one of these 23 water classes based on the cosine distance that we calculated earlier. So let's see how it stacks up. What we're going to do next is basically take the mean and standard deviation of all the pace spectra within each class. So everything in this class here, we're going to take a mean of all those spectra and see what the mean spectrum looks like, and we're going to retain the standard deviation information so we can make some little gray bars and see, all right, how much spread is there within that. So we'll do that for class 1, class 2, etc. Yeah, the pace spectra will sort of define that, and then we'll also plot the standard reference spectra that we pulled from our first 23 water classes as well. All right, it's also kind of a good sanity check. It shows whether our pace data are kind of roughly matching the expected shapes that we get, and then we get that aspect of variability. Okay, so let's take the mean and standard deviation here. We just to I think we already defined this above, and again, I like to keep some of this self-contained, so you can run these sort of independently. All right, so we're going to flatten the arrays again, so we can do the sort of basic math to it. And taking the mean spectra, what we're doing the flattening again, as I mentioned here, and then we let's see. I don't think we don't have to. We're not going to put it back in 2D space here because we don't have to, because we're going to make a plot, not a map here. So we can keep it in that vectorized space here. So a lot of this is plot formatting below. It looks large, but most of it is plot formatting. We're basically just lining up our 23 averaged water classes from PACE and our 23 reference spectra that we ingested earlier. In the background, we'll add and subtract a standard deviation and put it in the light gray, very aesthetically pleasing. And then we plot our spectra on top of that. And you can actually see as we run this that we get a, here we go. So we get a pretty good agreement between the average shape of our PACE spectra relative to the optical water classes. So which one did we define here? So the line style. That was a reference. Okay, the reference spectra are the dotted lines, and then the colored lines are the mean of all of these PACE spectra that fell within that class, and then you have the standard deviation in gray there. So you can, yeah, not a bad job. Although you can see class 18's got some kind of issues here, but kind of gives you a good sanity check of how well it's doing. Just for fun, let's kind of bring it full circle and compute the AVW, our apparent visible wavelength. Let's do that ourselves. Instead of grabbing it from the file, it's a pretty simple calculation, so we can compute it ourselves and just see how it compares to the water class assignments that we just made. It's a tiny bit of extra work here, but it's just this one line, and it helps you. It just kind of shows you how it's done, and that's also that it's flexible as well. We take a subset range of remote sensing reflectance. The apparent visible wavelength was built for between 400 and 700 nanometers, largely because that's kind of the range that it was sort of developed on based off of in situ data. But you can put whatever wavelengths you want in here if you want a little more idea of the spectral weighting in the UV or the near IR. You can extend this here, but by default it stays in the visible 400 to 700 nanometer range that we see up here. So we compute the AVW. And then we can compare the AVW and it runs near instantaneously there. And then we can go ahead and run the a cross comparison of the two. And you can see they largely mirror each other, but they tell you slightly different things. Optical water types here are giving you a concrete class for each pixel. So every spectrum in, say, class 16 is going to have a very similar shape. And that's great if you care about categorizing water masses consistently across space. On the other hand, AVW is kind of a continuous gradational measure with physical units. It has units of nanometers. So that makes it ideal for tracking sort of subtle changes over time. With AVW, you can literally say the color shifted by X nanometers over the course of a year or so many years. Because AVW is a weighted mean, any increase or decrease it directly reflects a proportional change in the overall color of the water, even if the sort of the detailed spectral shape changes. So it's essentially a classification versus a sort of metric or index distinction. Optical water types are categorical. AVW is slightly more quantitative in a sense. So sometimes the best way to kind of explore the data is letting it speak for itself as well. So instead of relying on the predefined reference optical water types that we've been using, you could do this yourself and use unsupervised clustering to see sort of what natural groupings exist within your image. So a really simple but powerful approach is through k-means clustering. This is what Jin Wei used in his paper. So we'll just try to kind of we're not exactly replicating what he did because he built his based off of in situ data, but we're just going to grab the same image and then build it based off of the reflectance in the PACE image here. So here's kind of the intuition here. Each pixel's reflectance spectrum is treated as a vector in sort of high dimensional wavelength space. So pixels with similar shapes end up in the same cluster, and that's why we end up normalizing the spectra first. That makes the clustering kind of focus on the shape of the spectrum rather than its absolute magnitude. Now you can try clustering the raw reflectance values without normalizing as well, but that can lead to sometimes many similar shapes kind of being split into separate clusters. It's worth experimenting with both approaches, and I'll actually show you both here. So we talked about the mechanics here. Most of this is just about getting the data into the right format. We need to flatten that 2D spatial image into a 2D array. So each row is a pixel and each column is a wavelength. And this is what k-means expect. So we also need to mask out any NaN values because it'll choke if it has any of those. So and then once that's done, we're ready to feed it into k-means, which as we talked about with the boosted regression trees is just kind of dangerously simple. But a couple of tips here: start with maybe a small number of clusters, 5 to 10, kind of get a feel for your data. You can increase the number to kind of capture maybe finer distinctions. At some point, you'll add so many and you're not really gathering much new information. There are statistical means of determining sort of what the optimal portion is too, but we'll just kind of tinker around for now. Also, here we're going to use normalize. So I set this, we'll try it first with the normalized data. So if it's, we just put an if statement in later. Oh yeah, here we go. So the X input here So we're going to use the RRS normalized, else we'll use just the non-normalized portion here, which we grabbed from earlier, that we defined this RRS subset common. That was right when we just compared the wavelengths with the reference data set and just grabbed the pace data. So our non-normalized and then our normalized here. And if you switch between this, it'll true or false, it'll use one or the other. All right. What else to mention about this? Fairly quick. So we've clustered our pixels. Let's take a little look at the results. First, we'll make a map, kind of, similar to our water class maps that we made earlier, just to show where each cluster falls spatially. This kind of gives us a visual sense of the geographic patterns, which clusters dominate in certain regions where the transitions occur. Next to the map, let's include like a little 2D plot of the mean spectral shapes for each cluster, and we'll put the standard deviation shaded around the mean, kind of replicating what we were doing before. So we'll just put it all in one plot to make it a little more compact. So it just helps us interpret what each cluster actually means in terms of light reflectance, which wavelengths dominate, how consistent the shapes are within that cluster. Okay, there's something here too. I added in here the changing the order for this. One thing that's what Jinwei did, he sorted the clusters in descending order of remote sensing this ratio of reflectance 443 to 551. You don't have to do that here. We could use something else or nothing at all. But if you don't try to sort of order your clusters manually, basically what you're going to get, it determines it, I think, semi-randomly. I'm not even sure exactly, based off of the sort of how it initiates. But cluster 1 will look nothing like cluster 2, will look nothing like cluster 3, and it's just kind of, it makes it a little hard to interpret. You could still link them to one another, but if you resort your clusters according to this ratio of reflectance, you can get it to look just like looks like this, to where you're kind of your blue waters to red. So it really helps a lot with trying to make things look a little more attractive. So all right, so let's go ahead and run these two. So together you can kind of see where and what the different spectral shapes appear on the map and what they look like spectrally. Almost all of this code is just formatting these plots. But a reminder here that we did our clustering in 1D space before, so we do have to reshape it back into that 2D space again. So yeah, here's our k-means clusters. Looks somewhat similar, and here's each of the 10 clusters that we pulled out. We can let's try false here. So we won't normalize the spectra, kind of see how things turn out. Changes the answer quite a bit. So it does kind of depend. These are, maybe a little bit similar to one another. If you normalize these shapes, they might look really similar to one another, all three of these, but this one is obviously quite a bit brighter than this. So in some cases, maybe it is a good idea to kind of separate these out and let the magnitude do some talking in itself. If we turn this up to, let's turn this up to 20 here, and keep in mind, yeah, we had the 23 optical water types earlier. That was a global parameterization. We're just looking at a small chunk of the North Atlantic here, right? So we're probably not going to have all 23 represented in here. So if we do too many types, we might have some pretty similar spectral. But I don't know. Even with the 20 clusters, it's not. There's still some kind of separation, but you see through the standard deviation, we're definitely starting to get some overlap between these. Yeah, that's how it works. Again, just if you wanted to really kind of do a robust means of this for a particular region, and you want to do this for yourself, we probably want to take many images, not just base it on one. You would want to basically ingest all the spectra across as many images really as you can get your hands on that represent all the different optical, conditions that you're likely to meet, and then run your clustering based off of those, and then you'll feel a little more reliable about using it into the future, that those shapes will indeed be represented. So yeah, you guys are all optical watertight masters now, and you can cut in front of line at any ocean color event, and then raise your chin with quiet authority over those who have not yet wrestled with water mass classification and spectral indexing here. So do go forth with your newfound powers and enjoy the ocean, and maybe impress a colleague of yours with your hard-earned spectral wisdom here.